Hey, I'm Dominique Piché-Meunier and I'm happy to talk about our work on depth of field estimation from images. Every photo is bound to have a certain amount of defocus blur, because modern cameras use lenses to focus the light on the sensor. This means that only some objects will appear sharp, those at the focus distance chosen by the photographer. The rays coming from those objects will converge to a point on the sensor. If the object was further away, however, the rays would focus at a closer point and would appear as a circle on the sensor, called the circle of confusion. This is the cause for defocus blur in images. Similarly, the object would appear blurry if it was closer than the focus disparity. The importance of this effect depends on some camera parameters chosen by the photographer, and in particular the size of the aperture. For a smaller aperture, or a higher f-number, the circle of confusion will be smaller and the image will appear sharper. If we were to draw the size of this circle of confusion as a function of the distance, we would get a curve that looks something like this, hitting 0 at the focus distance. If we drew it as a function of the disparity instead, which is 1 over depth, the curve becomes straight, like so, and if we assign a negative defocus to objects further than the focus disparity, we get a linear curve like this. We can thus model the depth of field of a scene using only two parameters, the disparity of focus, and the slope of this curve, which we call the blur factor, equals to the size of the aperture times the focal length. Our goal is to recover these two parameters from a single image. Most existing work related to this task only estimate a per pixel map of the defocus or the disparity. We could simply plot the signed defocus as a function of the disparity, which we know should have a linear form, and perform a linear regression. However, we found that this method sometimes lacked robustness to unseen images. To alleviate this issue, we trained a weight network whose task is to find the pixels where the defocus estimation is most likely to be correct, in order to give those pixels more weight in the linear fit. Even though it was only trained with a loss on the camera parameters, we found that the weight networks often highlights the edges and textured parts of the images, where we could expect the blur to be most easily noticeable. This helps increase the robustness of the estimated camera parameters. Finally, we can reconstruct a defocus map from those parameters and the disparity map, to obtain a smoother, physically correct defocus representation of the scene. In order to train the three networks, we generate datasets of synthetic and semi-synthetic images. For the SynthWorld dataset in the first row, we generate renders from synthetic 3D scenes using Blender cycles. In the bottom two rows, we apply the Bokeh-Me defocus synthesis method on real RGBD images, respectively from a proprietary dataset in the middle row, and on the DIML dataset in the bottom row. We show on the left some example results of estimated disparity maps on in-the-wild images. Existing methods trained on all-in-focus images tend to predict incorrect disparities for blurry objects, which is not the case for our method. Our disparity map is also generally more detailed, especially in blurrier parts of images. Finally, our method obtains the lowest disparity errors on datasets of images with varying depth of fields. Similarly, for the defocus maps, our method produces results that are sharper and seemingly more accurate than existing methods, due to our novel network architecture, our rich dataset, and our more intuitive depth of field representation. Again, we obtain state-of-the-art quantitative results for the task of defocus map estimation. But our final goal was to recover the two camera parameters, the disparity of focus, the f, and the blur factor, kappa. In the left table, we compare our method against doing a linear fit on the defocus estimation from other networks, to which we provide a baseline disparity estimation. Our robust joint method provides a much better parameter estimation. In the table on the right, we compare our approach with other strategies to recover the parameters from the 2D disparity and defocus maps, such as the baseline linear fit in the first row, or training a neural network to estimate the parameters directly in the fifth row. Our weight network in the last row seems to be the best strategy. Our lens parameter representation enables novel applications, such as the compositing of virtual 3D objects in shallow depth of field images. We compare our approach on the right with a naive composition using a pinhole camera model on the left, and a slightly better approach in the middle where we apply to the object a constant two-dimensional blur according to the estimated defocus map. The latter still gives unconvincing results though, as the two skateboard wheels exhibit the same amount of blur, even though the street is sharp under the front wheel and blurry under the back wheel. Our 3D approach gives a much more realistic composition, where the two skateboard wheels match the back wheel. Inserting the object in 3D is also much less cumbersome, as the camera parameters only have to be set once and the object will have a physically correct defocus, no matter its position in the scene. Thanks for watching!